Tonight on Machine Arena, we travel from rugged mountain roads to deep, precisely bored tunnels, following the unseen craft that makes rail corridors safe and fast. Clear visuals, plain engineering, and zero hype, the steps that keep people and freight moving. The first, in the crisp mountain air, we see a massive concrete column descending slowly from the hook of a crane. The weight is enormous, yet it moves with a deliberate grace, guided by steady hands on taglines. Below, a team of workers stands ready in front of a newly cut tunnel portal. Their voices echo in the gorge as they signal adjustments, an inch to the left, a touch forward, aligning the column with its footing. Once in position, wrenches click in sequence, fastening heavy bolts through pre-drilled plates. Each connection is checked twice, ensuring the column will hold its share of the portal's load for decades. The backdrop is a dark tunnel mouth framed by rugged stone, a reminder that this is just one piece in a far greater engineering puzzle. Then, the pace quickens. We cut to a sweeping montage of the wider work. Massive columns standing in a row, forming the skeleton of retaining structures that stabilize the slopes around the tunnel entrance. Trucks roll in carrying rebar, formwork, and pallets of precast segments. Forklifts weave between stacks of materials, staging them where they'll be needed next. Concrete mixers discharge into steel buckets that swing toward waiting forms, while compactors and dozers shape the surrounding access road. Deeper into the site, drill rigs bite into rock faces, boring holes for anchors that will hold protective mesh and shotcrete against the mountain's flank. Further along, workers in reflective gear guide sections of steel conduit into trenches, laying the groundwork for power and communications inside the tunnel. Sparks flare briefly as welders secure reinforcing cages, their arcs hidden behind protective screens. Excavators load rock into haulers, carrying it away in a steady rhythm. Surveyors stand beside tripods, confirming that each portal beam, drainage trench, and road alignment matches the exacting plans. In another shot, a blast is prepared. Small charges placed deep into the rock, detonated in a precise sequence, sending a controlled burst of dust and debris into the air. The final images return to the portal, now framed by completed columns, concrete slabs, and a cleared staging area. Every machine, every bolt, every slab of reinforced concrete has played a role in turning a raw mountainside into a stable gateway, ready for the tunnel crews to push forward, deeper into the rock. Now we step into one of the world's most exacting construction environments, a railway-based tunnel through alpine rock. The name of the game is alignment. If two headings, one advancing from the north, one from the south, fail to meet within a few millimeters, trains will feel it, track crews will struggle, and maintenance will follow for decades. Surveyors establish a control network linking surface benchmarks to underground points. Air temperature changes the refractive index, steel linings expand and contract. Even warm work lights can bend a sightline. So crews measure forward and back, then adjust the network by least squares math, until residuals shrink to almost nothing. Gyroscopic heading checks keep the azimuth true when a straight sightline is impossible underground. Excavation proceeds by geology. In strong rock, Drill and blast opens the heading. Jumbo rigs drill a fan of holes, charges fire in millisecond sequences, and powerful fans clear fumes before mucking begins. In uniform ground, a tunnel boring machine advances with a rotating cutter head, while hydraulic shoes grip the walls. Either way, crews install support immediately: steel sets, lattice girders, and fiber-reinforced shotcrete in drill and blast sections, or precast segments with gaskets and bolted rings in TBM drives. Because this is a railway, the finished cross-section is clean. Walkways and side ducts carry cable, water, and compressed air. At regular intervals, cross passages link the parallel bores, providing maintenance access and emergency egress. Caverns open for crossovers, equipment rooms, and ventilation. Fire hardening is built in. Low smoke finishes, hydrant lines, and protected refuge zones staged along the alignment. If a train ever stops, passengers must be able to self-evacuate along a level, illuminated walkway to the nearest cross passage. Track work here is ballastless. Instead of crushed stone, crews cast a precise concrete base called a slab. On top sit resilient fasteners that hold each rail at an exact elevation and gauge. The surveying team now shifts from meters to millimeters. Trolleys measure rail height and line. Grinders correct tiny irregularities, and expansion joints at portals absorb seasonal movement. Where the tunnel crosses faulted rock, elastic pads tune stiffness so wheel loads stay even, reducing vibration and noise for neighbors on the surface. Every system must coexist without interference. Drainage channels collect seepage and guide it to sumps for treatment. Vent shafts feed fresh air and carry heat out. The aerodynamic piston effect of passing trains helps, but fans are sized for worst-case scenarios. Power and signaling cables share trays with fiber optics, and the grounding plan protects equipment and passengers from stray currents. Lighting is uniform, anti-glare, and easy to maintain. Fixtures are chosen for long life and minimal dust buildup. Quality control is relentless. After lining segments are erected, lasers scan the interior to create a point cloud. Any bulge or flat spot shows up immediately. Concrete cores are tested for strength. Rebar cover is verified with electromagnetic gauges, and rail welds are ultrasonically inspected. Ventilation tests confirm airflow, and evacuation drills check timing to the nearest cross passage. When the two headings finally break through, the celebration is heartfelt, but it is also just one step in a series of measured checks. Precision carries into operations. Track geometry cars patrol the tunnel, measuring with gyros and accelerometers while rolling at speed. If the slab creeps, if a drainage trench silts up, or if a rail joint begins to chatter, the data reveals it long before passengers notice. Maintenance windows are short, carefully planned, and supported by nimble vehicles that can clear the route quickly should a rescue train need the line. Why does such fuss matter? Because high-speed trains ride on fine tolerances. A smooth alignment saves energy, reduces wheel and rail wear, and allows freight and passenger services to share the route safely. The payoff is capacity, more trains per hour, steadier winter performance, and fewer delays for the people and goods depending on this artery under the mountains. For those who grew up watching railroads bind towns together, think of a base tunnel as the 21st century version of a summit pass, only straighter, lower, and far safer. Its perfection is not flashy. It is the quiet craft of surveyors, miners, electricians, concrete finishers, and track crews working to the width of a pencil line, so every trip feels unremarkable in the best possible way. From high above, the camera glides over the yawning mouth of a station excavation, revealing a hive of activity deep below street level. Bright work lights spill across a cavernous space where machines and people move in coordinated rhythm. Tower cranes pivot slowly, lifting bundles of steel reinforcement into waiting hands. Farther along, a compact demolition robot nibbles away at an old concrete wall, its steady hydraulic motions throwing no sparks, just a cascade of rubble into a loader's bucket. Down the length of the chamber, graders and compactors smooth a bed of fill for the next concrete pour. The surface must be perfectly level. Every slab here will one day carry the weight of rails, platforms, and passengers. Vibratory rollers make pass after pass, their operators glancing up to signal survey crews stationed on the perimeter. In one corner, crews bolt together sections of formwork, their hammers ringing in the enclosed air. Elsewhere, welders crouch over frames that will hold cable trays and station signage. The faint hum of ventilation fans and the intermittent beep of reversing machines echo off the concrete walls. Supervisors in bright vests stand at elevated platforms, scanning the site and relaying instructions over radios. Their coordination keeps the demolition zone clear of lifting operations and ensures material deliveries flow smoothly from the surface down into the chamber. From this vantage point, the scale is striking. Dozens of workers, specialized equipment, and carefully sequenced tasks all unfolding beneath the city. Each action, from breaking an old slab to tightening a final bolt, builds toward a station that will serve trains and travelers for generations. Here we see the Rock 160 demolition robot at work, a compact yet powerful machine designed for tight, demanding job sites. Its yellow hydraulic arm fitted with a breaker steadily hammers into a reinforced concrete column. Each strike sends controlled vibrations through the structure, loosening chunks of concrete while leaving surrounding areas untouched. As the surface chips away, the embedded steel rebar is revealed, ready to be cut or removed. The operator, using a wireless remote, stands at a safe distance, guiding every motion with precision. Dust suppression sprays keep the air clear, improving visibility and safety. In minutes, the column is reduced in a clean, controlled manner, an example of how modern demolition combines raw force with accuracy to prepare sites for the next stage of construction. In this scene, the camera follows a crew performing a precise asphalt repair along a well-used roadway. It begins with cutting clean, straight edges around the damaged patch. The saw slices through the pavement, creating a defined rectangle that will lock the new material in place. Loose debris is cleared, and the exposed base is compacted to ensure a firm foundation. A truck arrives carrying a hot, fresh asphalt mix. Workers guide the chute, filling the cavity evenly. The asphalt is raked to distribute it across every corner, then shaped to match the surrounding surface. Compaction begins immediately, first with a vibratory plate along the edges, then with a roller pressing the center smooth. Each pass knits the new layer tightly to the old, sealing the joint so water and frost can't force it apart in winter. Once the surface is compacted to a uniform finish, a quick check confirms the slope will shed rain toward the nearest drain. The final touch is sweeping loose grit from the edges, leaving a neat, solid patch ready for traffic. It's a small job compared to bridges or tunnels. Yet work like this protects the approaches and access roads that keep heavy equipment, supplies, and commuters moving without delay. Railways often run beside irrigation canals. When a bank leaks or erodes, water can undermine the track embankment from below. One modern fix uses a dry concrete fabric, technically a geosynthetic cementitious composite mat that hardens after it is placed and hydrated. It installs fast, follows curves, and puts a skin between moving water and vulnerable soil. Watch the sequence. The crew diverts flow to lower the water level, then grades the bed and side slopes to a stable profile. Any sharp roots or stones that could puncture the liner are removed. Next comes an underlay to cushion the ground and protect the main layer from abrasion. Rolls of the cement-impregnated fabric arrive on a truck and are lifted into place with a spreader bar. Panels are unrolled down the slope and overlapped in the flow direction like shingles. Joints are fastened or sealed so water cannot lift a seam. Anchor trenches at the crest and toe lock the edges. Intermediate pins keep it tight so there are no voids. Crews trim around inlets, outlets, and control gates. Then check that the overlaps shed water cleanly and consistently. Only after everything fits do they add water. The cement inside the fabric hydrates and begins to cure, turning a flexible sheet into a thin concrete shell in a few hours. It resists UV light, weathering, and abrasion from sediment. Best of all, it installs with small crews and compact machines, keeping work clear of nearby tracks and power lines. For the people riding above, the benefit is invisible. Drier subgrades, fewer washouts, and less silt migrating into culverts. For maintenance teams, it is another rapid tool to keep a corridor open during the growing season, when farms need every drop. From a wide aerial view, the river winds below as construction crews prepare the site for a new bridge. The first steps are on the banks, leveling the ground, clearing access roads, and setting up staging areas for materials and heavy machinery. Excavators bite into the soil, grading the approaches that will lead to the bridge deck, while surveyors mark exact lines for each pier. Out in the water, cofferdams are installed to hold back the current, creating dry work zones for foundations. Steel reinforcement cages are lowered into place, followed by the careful placement of concrete. Each pier rises in sections, cured and checked before the next lift is added. From above, the symmetrical growth of these supports gives a clear sense of the bridge's span and alignment. Once the piers reach full height, large cranes swing prefabricated girders into position. Crews secure them with precision, bolting and welding connections that must handle decades of traffic and changing weather. Deck panels follow, set in sequence, joined and reinforced, while workers pour concrete to form a continuous surface. The finishing stages bring safety rails, expansion joints, and drainage systems to protect the structure. With the final inspections complete, the bridge stands ready, linking both banks with a smooth, uninterrupted crossing. From first grading to final tightening of bolts, this process blends heavy machinery, skilled labor, and exact planning. A modern river crossing built to serve communities and commerce for generations. From mountain access roads to millimeter true tunnels, from demolition to lining and resilient bridges, you've seen how each step supports reliable rail. Thanks for traveling with us. If you enjoyed this tour, like, share, and subscribe for engineering journeys.